Okay, and welcome everybody. Thank you very much for joining us. Good morning or good afternoon to you, depending on where you are situated. My name is Oscar. I'm the Sales and Marketing Manager for 3dprintingindustry.com, and I'll be moderating this event today. Today we'll be joined by Mantle and their Head of Marketing, Ethan Raito. And we will be discussing metal additive manufacturing for injection molding. But before I get to the main event, I'd like to just go over a couple of housekeeping areas for the show, which you guys can follow along with. So we're using the AirMeet platform, and this is an interactive event. So we'll be welcoming questions and Q&As from the audience, so that we can address these during the upcoming discussion. If you've already found the chat window, you can introduce yourselves there and speak among yourselves during the show. To ask a question to be answered during the Q&A, there will be a button up in the chat window marked Q&A. This is where you should post your questions for Ethan, and I will get to these throughout the event to make sure that we can answer them in a timely manner. A recording of the show will be made available afterwards to everyone who registered. So we'll be sending out this recording in case you missed the live event. Without any further ado, I'd like to invite Ethan Raito to the stage. Ethan, are you with us?
Hi, thanks, Oscar. Thanks for the introduction and thanks for hosting.
Yeah, good to see you. So I guess we'll start off with a small introduction. Just tell us a little bit about yourself, and then we'll get into it.
Sure. Hi, so my name is Ethan Raito. I'm the Director of Marketing at Mantle. My job is to really tell our story of what we're trying to accomplish at Mantle. I work a lot with customers on case studies. I do a lot of presentations and conversations like this, really to help people understand the value that Mantle can add, to show examples of Mantle, as well as helping to position our product to make sure that we're reaching the right people and that we're building the right product for what we're trying to do. And we'll talk a lot today about Mantle and what Mantle is trying to do. So thanks for having me, and thanks for giving us an hour out of your day today to talk about metal 3D printing with us.
Sounds good. Well, let's dive right in. Well, I guess a good starting point would be to learn a bit more about Mantle. So, I mean, if you could give us the thumbnail
Sure,
story, what the company is about, how it started, and
absolutely.
what you guys are up to.
Yeah, absolutely. So I have some slides that I'll jump in and out of here as it makes sense to it, depending on how the conversation goes. But Mantle is a very interesting company. Mantle was founded about 7 years ago by two co-founders, one of which is an expert in metal paste. Before I joined Mantle, I didn't even know that metal paste was a thing. But I guess there's a few select people, at least in the United States, that specialize in metal paste. And one of our founders, Steve Connors, is one of those people. The original application that he was doing was he was actually printing a silver paste, so a precious metal silver, that was connecting different electrical components in solar panels. So he was developing an application where printing silver, but just in 2D to connect different connections and trying to automate that for a solar panel application. He thought that was pretty cool. And then he actually thought, what if I could build a three-dimensional object out of silver? So he actually left that application that he was doing before. This was part of a Stanford research project, and he went to kind of explore on his own. Could I print a three-dimensional part using our silver paste that we're using in these solar panel in these electrical applications? And he was relatively successful. And that's when he met up with our other co-founder, who was very, very interested and said, well, I don't really see a ton of applications for 3D printing of silver, parts and bulky silver parts. What if we could do a steel? What if we could do a mild steel or carbon steel or even a tool steel? And that's kind of the foundation of what Mantle became. At a core, Mantle is a metal 3D printing company, but we are very, very unique in that. Let me just show a couple slides here. In that, let me show my entire screen here. Mantle is very unique in that we only target the tooling industry. We only target the injection molding industry today, but our goal is to print precision tooling. And by doing that, we've found that we actually have a printing process that is so precise, delivers the surface finish and the properties required for tooling, that we designed our entire system and our entire company simply to service this tooling market. A lot of that comes from our founders once they had this technology, going out and looking at what are the needs in the industry. We see so many 3D printing companies that they come out of labs, they start companies, they start selling, but they don't necessarily design their printer for an application. They design a printer, then they go and look for an application, which is a little bit backwards in my eyes. And I understand there's a lot of reasons that happens. A lot of it's because it's all coming from research in labs and research at universities. But Mantle is so unique in that we designed this printer specifically for this tooling application. Uh, and what that allows us to do is, produce, we'll look at some case studies later on, but to produce tools in less time at a lower cost and actually allow them to be more efficient. You can see our machine there on the right. That's our production machine that we just started shipping relatively recently, but it took us a long time to get to there. And I don't have a picture of our first generation system here. Um, but originally, we were printing these metal pastes. We'll talk about how those pastes actually work. Originally, we were printing them out of very, very low cost FDM printers. The printers you can buy on Amazon or you can buy really all over the place now. But we were able to print these metal pastes very, very easily through these low cost printers. We were doing this around the same time that some of these other MIM extrusion companies like Markforged and Desktop Metal were coming out with their systems. But we were doing this at that time, but we didn't really see a huge fit for that. Because the parts were relatively rough. They had some porosity in them. The tolerances were relatively poor. So we were thinking, okay, we can do this, but this isn't good enough. What can we do to make this better so it actually fits an actual application? The next thing we did, which is the second generation printer you're seeing here, was we added a shape refinement step to it. We'll talk totally about how our process works later, but Mantle's process is hybrid. So we are printing material and we're also CNC and machining it all within one printer. So in the second generation, we added that shape refinement in. Again, we had a relatively small footprint. We were using these relatively inexpensive FDM systems, but they were relatively unreliable. They weren't giving the tolerances we needed. They weren't giving the finishes we needed. So the next step in the Mantle story, the Mantle generation, was actually integrating our system into an existing CNC, which is what we're doing today, is that we're able to integrate printing and shape refinement into an existing CNC into a mill. So we're utilizing mills are designed to be incredibly reliable, incredibly precise. So we weren't going to reinvent the wheel there. We were going to integrate those machines to print our paste and allow for you to print tool steel. So a little bit of a long-winded answer here, but at a core, what Mantle is a metal 3D printing company that specializes in printing precision tools. We can produce the surface finishes, the accuracy, the properties required to print precision tooling, and I think that's very, very interesting to see. And you can see, even very, very early on, you can see a Mantle part there on the left that was printed on one of our early printers, but just the surface finish and crispness of the details we can get because we're leveraging those existing CNC platform, which of course you don't not see those layer lines and things like that. And we'll talk about how that works. But that really allowed us to design and build our printer that is kind of perfect for this injection molding application. We like to say this kind of idea of the precision of a CNC machine with the freedom of a 3D printer, which is kind of my little marketing tagline. But I believe it's really true, and hopefully I can prove that to you today as we're talking more about how this thing actually works.
Got ya. And I mean, in addition to all of that, very, very in-depth content there, were there any other factors that drove Mantle to go after the tooling industry as a specific kind of niche market?
Yeah, absolutely. So in my eyes, I look at where 3D printing has been, metal 3D printing specifically has been very, very successful in the past. Aerospace, space, medical device components, implants that go into your body. What do all those things have in common in my eyes? They're low volume and they're very, very high value. Tooling is one of these things that no one really thinks about, but the tools that are used to make everything that's around you, everything in your room, whether you're watching this on a laptop or on your cell phone, I'm trying to think of, my headphones here, every single one of these plastic parts around us ha- and metal parts as well, if you think about stamping and some of these other tooling applications, has a tool somewhere in this world that costs tens, even hundreds of thousands of dollars to produce those tools. You only need one of those tools or maybe a few over the lifetime of the product as they start to fail. But those tools are very, very low volume, very, very high value. So right off the bat, in my eyes, that's great application for metal 3D printing. The other thing was we looked at how other metal 3D printing technologies have attempted to address the tooling industry, and we've seen that traditionally they've really let that industry down. Uh, Tools need to be very, very precise. They use very specialized materials. Um, they have surface finish needs that most 3D printing methods couldn't hit. So we saw, okay, there's a great fit for 3D printing in general, and the current 3D printing market is not not servicing that industry well. The other thing that we could talk about is the lead times, the labor, of course, the costs, all really make it a really ideal application for us and an ideal application for metal 3D printing. It's also a relatively large market. So I think it was a really, really smart decision for Mantle to target this industry. But it's also an industry that has really, really high standards. When I first joined Mantle, I was thinking about when and visited a tool shop, right, that has one of our printers. And they
Mhm.
said, "Oh, on our tools, we hold tenths. We like to hold tenths." And I go, "Oh, tenths. So 0.1?" They go, "Oh, no, no, no. Tenths of a thou. So 0.0001." I'm like, "Oh, wow, this is a whole another level of precision we're talking about." So while it's a great application and there's a lot of need there, also really, really high standards, which has a high bar for Mantle to kind of achieve that. And later we'll get into talking about, I got a bunch of tools here on my desk that we could talk about and look at. But really, really, we get you pretty close. I like to say that we get you about 75 to 85% of the way there on our tools, but all of this is right off the printer, right? So you're not seeing those layer lines or any of those, surface finish is quite incredible. Really, really crisp details. And we'll talk some more about applications later.
No, thank you for the explanation. Yeah, looking forward to getting a bit more into it. One thing you did mention earlier was the use of metal pastes and the ability of Mantle to produce these highly precise tool steel components. So, could you maybe elaborate a bit for us on how this technology works and how you're using it?
Sure, absolutely. Um, I'll go through now and kind of um, explain how our technology works. I'm also just seeing a question here. I would love to make this as interactive as
Oh, yeah,
possible about
absolutely.
MIM type parts / printer. Isn't MIM metal injection molding? What is a MIM printer? That's a great question, and let me clarify that now. So MIM absolutely is metal injection molding. What people have done over the past 5 to 10 years, and it's similar to what Mantle is doing, is have found ways to print those MIM powders. So there are a couple different methods of doing this. Where one of them we're using a paste. Some people use that MIM powder and mix it with some binder or waxes to create a filament or to create a rod, and then they actually print that MIM material. So they're printing that combination of metal powder mixed with those binders to achieve their green body. Then they put that into the furnace to sinter it, but they're still getting that 20% shrink that you see in MIM, even potentially higher. They're getting some porosity and some challenges there. So that's a good question there. So there are metal injection molding, or MIM implies metal injection molding, but there's these MIM-based processes that utilize the same powders but printing instead of molding. So hopefully that kind of answers that question, and that's kind of a perfect segue into talking about how our process works. As well. Let's see here. Let me share my whole screen here. Awesome. So hopefully everyone can see that now. So as I mentioned before, and this will get into kind of talking about our paste as well. Our co-founder is an expert in metal pastes, and pastes are very, very interesting because it's almost like a concoction, right? Where we can create these pastes by mixing together these different building blocks to achieve exactly what we want to achieve. So this is kind of some of the real secret sauce in our technology. It's one of the really key things that allows us to do what we do. But we create these pastes that are essentially a combination of these three different building blocks. One of them is metal powders. These powders are very similar to what you would see in the metal injection molding industry. So we get different steels, different alloys, and we can mix them together to create our paste. We're going to mix a little bit of binder in there. Binder is like a glue. It just helps hold the part together while it's being printed. And then some solvents. The solvents allow that material to flow and to be printed. So this paste kind of has the consistency of a toothpaste that you would squeeze out of your toothpaste. But what it is a combination of metal powder mixed with binder, a little bit of binder, and mostly solvents to allow it to flow. One of the key advantages here is that our paste is then going to be fully encapsulated. It's going to be fully, there's no loose metal powder because it's all mixed in with this solvents and this binder. So you don't have to worry about any of the hazards that come with loose metal powder, which is something that tool shops and molders love to hear, because bringing a metal powder into your facility, it comes with a whole lot of different standards that are quite challenging. So we start in our paste, then we go and we print this paste. Our printing step is very similar to the FDM process or FFF process that you would see, all over the world, and with many different plastic 3D printers or some metal 3D printers, where we're actually not even heating our material, since it's so easily flowable. It's viscous enough that we simply just pump it through this needle and lay it down layer by layer. At this point, we still have that combination of metal powder mixed with solvents and a little bit of binder. After that step is complete, this is all happening within the printer. We come through and we dry every single layer. What's happening when we're drying is we're actually firming that layer up a little bit, so it goes from being like a toothpaste into kind of like a dense foam. So we
Okay.
remove that solvent, and there's still a little bit of binder left in there just to kind of hold the part together. But what that allows is for us to have a very, very high green body density, and we'll talk about why that matters a little bit later on. But
Mhm.
essentially, what that means is the part is mostly metal powder and it's very densely packed. After that, we're going to come in and machine the part and shape the part. So we come in and we actually machine the part. We actually refine the features. We mill every single layer flat. Every 10 layers, we're going to come through and we're going to contour mill as well. But since the material here has the consistency of like a dense foam, we can machine it very, very quickly and at quite high speeds with very, very small cutting tools because it's just a soft foam at this point. It's not a tool steel yet. It's not a steel yet. uh, that's going to be repeated every single layer. So every single layer, all within our printer, we're printing, we're drying, and we're shaping. And I'll show a video about how this works in just a little bit here. After that is complete, we're going to go into a furnace to sinter. If you're familiar with sintering, you'll know it's widely used in powder metal applications like metal injection molding or press and sinter. But the sinter process, essentially, you can think of like pottery, right? If you go take a pottery class on the weekend, you shape your pot on your wheel, you're molding your clay, you put it into the kiln, and it comes out hard. Similar process here where we're heating our metal powders to just below the melting temperature of the material. It's going to remove any of that binder that's left in the part. The part's going to shrink about 9% in this process. So the part does shrink a little bit. That's a very, very low shrink rate if you're familiar with metal injection molding or other sinter-based processes. That's because of that very, very high green body density. The part is mostly metal powder in this state and very, very dense. So it doesn't need to shrink much to close up all those pores. So what comes out is a tool steel part. You can see I have some parts with me here on my desk. What comes out is a dense. Oh, hopefully you can hear that. That would probably drive a toolmaker crazy that I was doing that. But what comes out is a dense tool steel component that can then be used for molding, can be used for a variety of different applications with little to no processing. And you can see, hopefully you can see. I don't know how well this camera is it's coming across on my camera here, but you don't see those same layer lines that you would see with traditional processes because we've come through and we've machined and we've removed those layer lines. We
Mhm.
can do these very, very fine features. You can see some like the threads. I don't know how well that's coming across, but we're able to add in those very, very fine features because we get that resolution and accuracy that you would get with CNC machining. So we get those very, very fine features, some tiny features, as well as that excellent surface finish. Um, just want to show quickly. I hate showing videos and presentations, but I think just to get the point across, you can see.
Yeah.
I'm sure it's probably a little choppy, but laying down that paste material here, so that's that combination of metal powder and solvents. We come through and dry to remove those solvents out. And this is all happening within our printer, which is, as you can see, is a CNC. We then use those same cutting tools to come through and refine that shape and touch up both features as well as improve the surface finish, etc. Then I'll quickly show a video. This is actually producing this part that I'm holding here. This is a mold for a medical handle tool, but I'll show a quick video of the sintering process as well. Ooh, wants to play again. And a little harder to get a furnace into or a camera into a hot furnace. So this is an animation here, but essentially we're just uniformly heating and cooling this part to make sure it densifies very, very properly, and that's how we're able to turn it from a paste into a tool steel. Long-winded again, sorry, Oscar, but
No, no.
it's a lot to talk about with our process, and I could talk about it all day.
No, very nice and very informative. And I think just before we go ahead, I saw a couple of questions from the audience
Sure.
members, so we can get to those. And just a quick reminder to everyone: if you do want to get involved with the Q&As, just be sure to use the Q&A section, so we make sure not to miss your questions. So a couple of questions here. One user is asking, have you explored extruding profile shapes?
We have. So this is another precision tooling application that we're just starting to explore, but we just recently completed a pretty awesome trial that I'm working on a case study now on, and I hope to have that out soon of some extrusion because they have the same needs, the same challenges. They need precise tools, they need tool steels, they have the same requirements. So extrusion is actually a really great application for us. So we have done we're starting to do some extrusion, and we think it's going to be a great market for us.
All right. Guess we'll have to stay tuned then.
Yeah.
And then another question that was interesting was just asking the difference, or if there is a difference between mantle powders used and metal injection molding powders when it comes
Yep.
to size or distribution, things like that.
Yeah, so I'd have to confirm with our material science team and our metallurgists. I'm sure a lot of that honestly is proprietary to the exact powders we're using, but I do know that we use a range of powder sizes to ensure that, I like to think of it as if you imagine you had a big bucket, right? And you started by putting in some volleyballs, then tennis balls, then golf balls, then marbles. The goal
Yeah.
is to have the highest green body density possible, which means you want to use a lot of different particle sizes so that they can fill different shapes and there's not a lot of in the green body, there's not a lot of porosity.
Mhm.
So I know we use a broad spectrum of different powders. I don't know about the specific shapes and sizes and things like that. I'm sure honestly that's proprietary because we wouldn't want anyone to be able to just copy our paste material, because that's one of the big the keys for us.
Fair enough. Makes a lot of sense. And one more before we move on. Somebody was asking how long the sintering process is typically.
Yeah, sure. So the sintering process depends on the part size, but it'll be anywhere from 24 to 36 hours, depending on the part. The reason that that cycle takes so long is usually the cooling rate. As you can imagine, our furnace has a peak temperature of 1400 degrees Celsius. Uh, the part, I believe, sinters closer to 13 to 1350 Celsius. It only spends about an hour to 2 hours at that temperature, and that's when the actual sintering is happening. You don't want to take a metal part from 1350 Celsius to room temperature in an hour. The
Yeah.
part's going to do some crazy things and do some crazy warp and things like that. So we have to very, very uniformly cool the part. The other thing is you do not want or cannot have any air inside of that furnace, because the part will oxidize, it'll rust. And when something's very, very hot, you cannot expose it to oxygen like that. It's like welding, right? That's why you're always flowing gas over when you're welding, because the
Mhm.
metal's getting hot and you wouldn't want it to oxidize. So we flow nitrogen in our furnace, but without the absence of air, you're not able to get that convection heat transfer. You're not like you can just blow a fan on it to cool it down. So that makes the cooling times even longer. Some furnaces do some cool water cooling things and things like that. And I'm sure we'll innovate on our furnaces in the future. But for now, it's a 24 to 32-hour cycle. But just to know that that's batch. So I could put a couple of these in the furnace at once, because it's just a batch process, just like
Yeah.
you're using your oven at home.
Yeah, and you're slashing lead times like crazy anyway. So
Yeah,
nice. Cool. Well, I see a couple more questions rolling in, but we'll keep the event moving, and then we'll get to those at a later point throughout.
sure.
And I guess yes, we've had a nice look at the tech and a bit more of an understanding from you on how it works and what it's made to do. So now I guess it'd be interesting to move on to hear a bit on how people are using it. If you have any sort of case studies or customer stories on how people have been leveraging this
Yeah,
technology.
absolutely. So I'm trying to think of what's the best case study to show here. Let me start with our customer, Nicolay Plastics. Uh, Let me share this screen here. I think I'll actually walk through this whole case study. So Nicolay Plastics is an injection molder. So at their core, their goal and what they do as a company is they mold parts. They're shooting plastic. They mold millions of parts a year. They have facilities all over Wisconsin here in the United States. They have a lot of different presses, and they just recently invested in a mantle machine. 3D printing is not new to Nicolay. In 2019, they invested in a carbon printer. That's a DLP machine, a resin-based machine. If you're not familiar with it, a pretty interesting machine. It promises to produce plastic parts very quickly, and also to produce parts with the finishes and surface finish. Their goal was to really replace the low end of injection molding, a couple hundred parts, maybe 1,000 parts, without the need for a tool, what we're doing to produce. So what that allowed Nicolay to do was to provide their customers parts in hours, not weeks, which of course has their advantages. And they saw that this was a great addition to their business, but at their core, they were still an injection molder. They're making all their money doing injection molding, and for injection molding, they needed tooling. They have a decent tooling operation at Nicolay. They can do hundreds of tools at a time. They have a full service tool room. They do both external and internal tooling with those both domestic and offshore tool makers. But as we've already talked about today, and if you worked with tooling in the past, you'll know that tooling comes with lots of challenges. When we talk to Nicolay about their tooling challenges, they say very, very long lead times. When a customer comes and wants to start molding a part, maybe they have the plastic design, it can be 6, 8, 12, 16 weeks before they can start delivering parts to that customer because it takes them that long to build the tools or to get them from an outside supplier. Costs tens of thousands of dollars to hundreds of thousands of dollars to produce that tool. And to really service this lower end of volume, maybe someone only wants 1,000 or 2,000 parts, very, very, very challenging because of these lead times and costs. No one wants to wait 6 weeks and pay $10,000 or $15,000 to only produce 1,000 parts. So it was very, very hard for them to service this kind of lower volume end. The other thing we haven't talked about too much today, but it's very, very interesting, especially here in the United States, is the absolute labor shortage that's happening around skilled labor across manufacturing in general, and especially when it comes to tool makers. Nicolay, I believe, has a tool room of 5 tool makers. The most junior, the one that's been there the least amount of time, has been there for over 20 years. So just to show that there's not a lot of tool makers in this country, and when you have one, you hang on to them, because we talked to a lot of people that say, when our tool makers decide to have a retirement party, we are going to be in trouble because it's that hard to find them today. Um, so the reason that Mantle decided to, or Nicolay decided to invest in Mantle, is they feel that Mantle allows them to produce production tools in prototype time, which is very, very interesting. They can print inserts that are 75 to 95% of the way complete with minimal to no user interaction. It takes about an hour to put an hour of your time to put a part through the process. If you're familiar with molding and know about injection molding, generally our insert, this is actually Nicolay's insert right here. All they had to do to this insert was a quick grind to the outside just to fit it into the mold base, and they finished these ejector pins just because, as you know, ejector pins are so precise that they just had to finish it a little bit with wire EDM. It also allowed them to free up their internal toolmakers to work on other projects, since their toolmakers only had to touch it once it reached this point. You can imagine all the work that would have been required to build this traditionally, but they get
Yeah.
this out of the furnace, and they can just do the little bit of finishing time to finish it up. The other really interesting thing that Nicolay says is, I think with 3D printing, and Oscar, I'm sure you've heard the same. It's so common to talk about 3D printing and talking about, oh, it reduced my lead time. It allowed me to produce it less costly, reduce the cost
Mhm.
on existing things. But very rarely do you talk about 3D printing with, oh, it actually allowed me to expand my business, to open up new opportunities, to grow my revenue. Everyone always wants to talk about, how can I make the things I'm making today cheaper and faster? Nicolay is very interesting, is that they feel that Mantle is actually opening up an entirely new side of the business for them, because now they can get involved with their customers very early on. Before, if a customer came to them and said, I want to mold 5,000 parts, Nicolay would say, sorry, we're not interested. We can't justify it, or it's not a good fit for us. Now they can do that. And that, which one, that opens up new business for them, which is great. But what's even more important is that by getting involved early with them in that stage, when that customer then wants 1,000,000 parts, they're also going to come to Nicolay because they already have the tool. Which, that's where Nicolay is very, very interested, because that's where they make all their money. Sure, it's
Mhm.
great to produce 1,000 parts for you, but we want to sell you 1,000,000 parts. So that's really, really interesting for them, and they see that as a huge strategic advantage to be able to get involved with customers on the early side. Of
Yeah.
course, they can also offer things like conformal cooling, which maybe we can talk about later, and increase the capacity of their tool room to produce more tools, because their tool makers don't have to touch these tools as much. They're, pretty far along. Uh, so the part I have here is actually for like a little latch. It goes onto the dashboard of like a police vehicle. As you can see on the part, it has a bunch of these thin ribs, a bunch of different angled faces all throughout the part, which made it pretty challenging to produce the tool. The tool would have required a lot of sync or EDM work, if you're familiar with that, of burning these features because of these thin ribs and these aspect ratios that you can't machine. So what they did was they printed 3 different inserts. They can see one. This is the insert I have with me up here. This is one side of it here, the other insert on the bottom. And then they actually dropped in a third printed insert, that they did that because they needed to do some special venting situations. So all 3 of those inserts were able to be printed in about 150 hours, so about 1 week here. And then they were all in the furnace for about 36 hours. But of course, that's with little to no user interaction. Then those parts went through about 10 hours of finishing. I'm trying to get to my slide here, where you can see ultimately what this meant was the top was what they would have had to do if they were producing this tool traditionally. From sourcing raw materials to doing all the programming work for the CNCs, for the EDMs, for the mills, to actually program how these parts are made, to do the rough milling, the electrode milling for each different feature that they were going to burn via EDM. They'd have to design, cut, and burn electrodes. And then, of course, all the finishing involved as well. So they felt that they went from 180 hours of active time down to just 12 hours with Mantle. Of course, there was still printing time and sintering time involved, but all of that was done unattended and all of that was done in the background. So you can see here that they went from a lead time of 6 weeks down to just 2 weeks. So 2 weeks to produce to produce a mold, an H13 mold, is pretty incredible. This was also molding a 35% glass filled nylon, so a very abrasive material. And the tool, they've done thousands of shots. They're still running the tool. And they're very happy with the result here. So this is just one good example from Nicolet where they're saving time, they're saving costs, but they're also expanding their business because now they can take on work that they wouldn't have been able to do before. Again, a long-winded case study there, but once I get started, I just keep rolling.
No, very interesting, and I mean it's really revolutionizing and streamlining that very much traditional industry, which is definitely in need of a change. So that's great. So I guess a follow up to that would be, we've looked at all the huge benefits that this process is bringing to the tooling and molding industry. But are there any sort of limitations to the process, or any features within a mold or types of mold that
Sure, yeah.
provide a challenge?
Yeah, so I would love to say no, there's no limitations, but unfortunately, we live in a reality. There absolutely are limitations. The first I would say is we are not a good fit for everything, and I think that that's something that all of 3D printing should know, and everyone that's looking at 3D printing should know that just like traditional methods, there's casting, there's forging, there's molding, there's MIM, you're going to use the right method for the right part. For the right parts, we make a lot of sense. And generally, what those parts are parts that are around this size or around this size. So, kind of like the size of my palm of my hand here. And parts that have a lot of feature, a lot of definition in them. A lot of these thin ribs, parts that would traditionally require a lot of sync or EDM. If a part can be made traditionally just via CNC or can be made in 10 or 15 or 20 hours, you should keep making it that way. That's great. We are great for the tools that take hundreds of hours to 200 hours because of all the EDM work that's involved. So that's the first thing I would say is that we're not a great fit for every tool, but for a lot of these small to medium sized tools that are medium to high complexity, that's a great fit. Of course, we have a size limitation. Today, our print bed is 200 millimeters by 200 by 150, so that's about 8 by 8 by 6. Um, the bigger challenge with printing big parts is not so much can you print them, it's also can you sinter them. As we talked about earlier, the parts shrink about 9% in the furnace, which is relatively low for shrinking in the furnace, but that still can be challenging when you get to big geometries, right? Because shrinking 9% of 50 millimeters is a lot easier than shrinking 9% of 200 millimeters, where the part's moving quite a bit. And while it's moving, there's a lot of opportunity for distortion or to lose tolerances and things like that. The other thing I would add with size is that with the bigger the part gets, the longer it takes, right? So when you're printing something that takes, this may take maybe 50 hours or 60 hours, so two-ish days,
Mhm.
great. But if you have something that's massive that takes 7 or 8 days to print, maybe you start to lose some of the value. So it's all about the right parts and the right geometries. The other things I would say is aspect ratio. We try to withstand a 10-to-1 aspect ratio. We can do some really intricate features because we're able to machine in layer, which is very interesting. And then things like we struggle with, not struggle with, but like we have to teardrop shape our cooling channels and things like that just to prevent them from drooping or falling, which generally isn't a big challenge.
All right. All right. Well, I see the Q&A section seems to be lighting up a
Great.
little. So maybe we can come and address any of those. I see one coming up asking whether the green unsintered part can be machined as well as the finished part, or if you'd only be
Yeah,
working on
so
the finalized.
the green part is machined. That's kind of what our secret sauce is the green part is printed and machined every single layer, which is why we're able to end up with a green part that doesn't have layer lines. It has very intricate features because we can print relatively coarsely, kind of oversized print, and then come back and machine every single layer. If you need to machine the sintered part, absolutely can. We're very proud. Let me actually just share something here. Um, yeah, this is great. We're very proud that we've put a lot of work into ensuring that our materials perform identically to a traditional steel. So you can see here, this is an insert that we sent out to a machine shop. We asked them to, can you grind it? Can you machine it? Can you sinker EDM? Can you do wire EDM? Can you tap it? Drilling? All of that was able to be done without any changes to standard operations, because we totally understand that for a lot of applications, they're going to need to do a little bit of work. You're going to need to tap some holes, or maybe add some threads, or maybe do a little bit of grinding just so it sits perfectly. So you can do all of that. You can do the texturing, plating, polishing, welding. All of that can be done to our tools as well, which is really, really great. While I'm here, I just want to briefly talk a little bit more about our materials. These are not just prototyping materials. I think it's very, very common with 3D printing and tooling to talk about prototyping. Oh, we're going to mold 5 parts, 10 parts, 20 parts. This is an example from Tessie Plastics. This is actually the screw that's used in your deodorant stick that hopefully we all used this morning. You twist this and it advances your deodorant throughout the tube. So this is actually an interesting story in that Tessie Plastics has a 64 cavity mold. So there's 64 of these molds all at once molding this part. So every time that mold opens, 64 of these pop out.
Okay.
During COVID, people weren't buying as much deodorant because they weren't going out. So they actually stopped running the mold. They shut the mold down and they said, we don't need to run this right now. The demand is not that high for these parts right now. So during that process, they said, oh, this is actually a good time to evaluate mantle. So they asked us, can you print us one in your P20 material, one in your H13 material, and we're going to put them into the 64 cavity mold and see what happens. Let's see how it works. So we're very, very proud of this case study because after 1.65 million cycles, and I think it's been a year and a half now, our inserts are still running. They're still producing these parts every day. That number keeps going up as this tool opens and closes every single day or every couple of seconds. And they've seen no unexpected sign of wear on this tool. So we're very, very proud of this case study with Tessie that showed that our H13 and our P20 materials were as accurate and durable as these traditional inserts that they were using before. So it's obviously we can do the prototyping, we can do the bridge, but when you're ready to go to production, you can absolutely do that as well.
All right, very nice. Another user is asking whether the system uses a positive displacement pump with the screw to kind of dispense the material.
I don't know the exact pump that we use, but I know we are using a pump that's just literally pumping our material comes in a tube and we literally just pump it through a hose into the nozzle. I don't know the exact pump that we use, but we don't heating, we're just pumping. I don't believe we don't use a screw to actually advance the material. It's just being pumped.
All right.
So beginning of the print, right, it's going to purge a little bit just to make sure it's there and ready to go.
And then a few users have been asking if there's also a print service available via Mantle.
Sure.
If they try out the
Yeah. So another thing that I like about Mantle and I think is just smart for 3D printing in general is that we do not want to compete with our customers, right? Our customers are buying these printers to print tools and to mold parts for their customers. So we as a company, we do not sell inserts. We don't print parts for anyone. We certainly print parts for you if you want to do an evaluation or you're looking at the technology. We're happy to do that. But if you're looking to buy just printed parts from our technology, we'd be more than happy to introduce you to one of our customers that's doing exactly that. So today we're not a service provider. We sell equipment. We sell the machines. But just to caveat that again, if you're looking to evaluate the technology, feel free to shoot me an email or a call, and you can send us a file, and we can print that for you as part of that evaluation.
Right. Well, let's move on, and then we'll get to the rest of the questions.
I'm just looking at one more question here. I'm
Go
seeing
ahead.
a couple of people asked about the price. We're also very proud of our price, so we share that pretty publicly. It's on our website. Our system all in is roughly 350,000 USD, and the reason for that price point is we designed this system to be very comparable to the high-end machining, the high-end EDM equipment that tool shops and molders are already buying. So it's designed to go into your tool room. It's designed to be priced for your tool room. So it's about $350,000, and we like to get that out there because a lot of people think of metal 3D printing and they think of 800,000, 900,000, $1 million machines. We're designed for the everyday shop, for the everyday tool maker, or for a lot of them, I should say.
All right. So I guess we've talked a lot about how Mantle is kind of addressing a niche in the traditional manufacturing kind of sector. Would you say that the system is designed to fully replace these traditional machines, or is it kind of designed to complement people's operation and to be used as a new tool?
Yeah, so I would absolutely say it's designed to complement. Um, Most tools, if not all tools, are going to require a little bit of work afterwards. Usually it's just 5 to 10 hours of doing some grinding. You can see like on this insert here, right? They just did a little bit of grinding to the outside just to make sure it's seated perfectly inside that mold base. So very much designed to work alongside your traditional equipment. But what it allows you to do is essentially at the push of a button, get you 75 to 85% of the way there, which that's the real value we see we're adding is that with very, very little labor, very, very little interaction, we could get a tool that's 75% of the way there. And a lot of tool makers would much rather start from this starting point than from a block of tool steel that's very, very difficult to hog out of the machine. So
Mhm.
certainly not replacing. We're very much complementing. We're allowing you to, expand your throughput, to expand your tool room, to do new geometries, to really do all sorts of different things.
Nice. And then I guess my next question would be looking at the material side of things. I guess in any industry, they are a key, backbone to how these industries operate, um, and very critical in any 3D printing application. Could you maybe share a little bit more on sort of the Mantle strategy for material development, and kind of I guess the tool steel is one, but if there are any other ones
Yeah,
that you're
sure.
working on or leading to.
Yeah, sure. So our materials are very much um, driven by our customers, right? By the needs we see, by what we're asked for, by the markets we see potential for. So originally, when we started the company, the first material that we announced was this P20 stainless steel. P2X is what we call it. Ours has a little bit different chemical composition, but it performs similarly, but has a little bit improved corrosion and abrasion resistance to a P20. P20 is a very, very common uh, lower volume mold material. It's above aluminum, but it's below H13, and that it's great for a couple thousands, tens of thousands, even hundreds of thousands of parts if it's a commodity resin. So we started with the P20 because we thought that's where we're going to fit in really well. The next material we came out with was this H13 material. H13 is commonly known as kind of a workhorse material for production grade tools. It can be used for millions of cycles, if not more. It has a much higher hardness, so it is great for these very, very abrasive materials. And interestingly enough, once we announced our H13 material, everyone that was using the P20 was like, oh, we just want the H13 now because for us, they cost the same, right? So if they're going to cost the same and your tool is going to cost the same, they go, why would I not use H13? The reason we don't use H13 is because it's usually more expensive or it's harder to work with. But since all the work's being done in your machine, let's just use the H13. So most of our customers today are using our H13 material. We do have that P20 material if people are interested. The next material we're going to be releasing is going to be a 420 stainless steel. That's a very interesting material because it's a high hardness stainless, which is really, really good for corrosion. And it's also really good for the medical device industry, which we do a lot of work with the medical device industry because of their ability to sanitize it and its corrosion resistance. They're very, very interested in the stainless steel. So that's the next material on our roadmap. Going forward, going to be very, very driven by our customers. What are our customers asking for? What are people asking for? Do they want an S7? Do they want a different material? We're also looking at some of these new applications like die casting or stamping that require maybe a D2 or an A2 or some of these different materials. But we certainly have a lot we can do with our printer and our pace, and I'm very, very excited for the future of our materials here.
Nice. And I guess while we're on the topic, a quick question that's come to mind is the sort of what kind of sinter densities are we looking at with the mantle parts?
Yep.
After all this.
So we achieve a 97% and above density, which we feel which we have proven to be fully adequate for molding applications. As I've shown you, we've molded millions of parts, abrasive resins, high temperature resins, fully adequate for that. One thing that a lot of people worry about with porosity is pitting. Pitting is when you were to polish your part or to machine your part or grind your part, that you would start to see that porosity and make it impossible to achieve a better surface finish. This is very true of a lot of other 3D printing methods that even if you look closely when it's polished, you'll never get that perfect surface finish because you're going to start to remove material, you're polishing it, but you're starting to see porosity within the part. We
Mhm.
do not see pitting within our parts, which is really, really critical. And that's why we're able to achieve this A2 surface finish. if you need to, you can polish it to a higher surface finish as needed. So again, long-winded answer there, but 97% and above dense, and we're not seeing pitting in the process when you grind or when you polish it.
All right. Very nice. And then I guess maybe just diving a little bit more into the use case
Yeah, let's
things.
do it.
What are some other ways the customers are using the Mantle technology? Are they mainly using it to kind of prototype? Well, I guess not, but a lot of
Yeah,
prototyping tooling, or are they also using it for things like conformal tooling and building
yeah.
conformal tooling and building that into their parts?
I have a couple interesting conformal cooling case studies we've done. I think with 3D printing and tooling, it's been so common to talk about conformal cooling almost always, mostly because that was the only way you could justify that sort of high cost of the tool that we would get from a laser system or a DMLS system was, okay, we're going to have to do some crazy cooling channels to justify the high cost and the longer lead time with those systems. What's really, really interesting with Mantle is that we are already producing tools that are faster and less expensive without using conformal cooling. So conformal cooling is kind of like the cherry on top, right? You can add that to your tools that it's not adding cost. You can get conformal cooling without a time or cost penalty, which is really, really game changer for a lot of these companies because, of course, with conformal cooling comes faster cooling times, increase your press capacity. One thing that I wasn't aware of before I joined Mantle, but different resins and different shapes, they have some issues with cooling and shrinkage, but being able to moderate the temperature of that tool and keep that tool at a very precise temperature really helps with your molding quality. So we see a lot of customers that are interested in using conformal cooling. Yeah, sure, it's great to reduce cycle times, but it's also great to allow them to produce better parts, reduce their scrap rate, and get better dimensional tolerances shot after shot because the tool was a very, very uniform temperature. It's not heating up and cooling as you're using it. They're able to keep it at a very, very precise temperature. One cool example here, this is from Westminster Tool, our customer here in Connecticut. They were able to reduce cycle time by 25%. They were able to save 25% of their attended manufacturing hours versus traditional. And just so awesome here is that ability to do this insert. It's a 3x3x2 insert. The entire insert was within 0.002 inches of the spec, so of the print. So right out of the printer, it was incredibly precise. Again, you can see they did a little bit of grinding, or they grinded the outside just to make sure it was perfectly seated, but they left all this feature detail as printed. And you can see that's the sound of the surface finish you get right off our machine or right off our printed inserts. Another very interesting one was with PepsiCo. This is a blow mold, so an application for building a bottle. I don't know if everyone's familiar with blow molding. I certainly wasn't before I joined. It's really really cool process where you kind of put like a sleeve into the tool and you blow air in it and it expands into the tool. So that's how they make bottles. If anyone's drinking a Pepsi right now, you can look at the bottom of your bottle and you can see there's somewhere in the world there's a tool that looks just like this. It's probably not our tool yet, but they're looking at our tools. And they were able to use a conformal cooling spiral in the bottom here, which actually helped with some mold defects they were having. They were getting some blushing from the heating. They weren't getting the plastic as clear as they would have liked it to be. And they, from just 9 days from design to completion of this tool, with that conformal cooling channel in it, and you can see that they did minimal machining. They just had to grind. I got a typo here. Grind the top and the bottom, and they did a little hard milling to the. There's a O-ring seal here for the actual channel. So really, conformal cooling is an awesome application, but it's not a requirement for using our technology, which I think is really cool. That a lot of companies see it as a bonus that they can then go and add on to tools that they're already delivering faster and less expensive.
Excellent. Well, yeah, I mean, that's obviously very interesting to people in the kind of injection molding and tool making industries. But what about sort of OEMs and companies in that kind of sector? Are you seeing any uses in that area?
Yeah, absolutely. So uh, our kind of key verticals that we talk about a lot and we look at is there's molders, right? People that are molding plastic parts. Those molders either do some tool making themselves or they are buying tools from a tool shop. The other market for us is tool makers. So people that are just all they do is build tools. They don't do any molding. They build tools all day long. And then the third would be an OEM that's vertically integrated. There's actually a decent amount of OEMs that do some level of molding themselves. A lot of those are in the medical device industry, as I mentioned, and the reason they do this is usually for strategic purposes. That being able to have that ability to manufacture in house, they see as a strategic advantage to increase their speed, to lower their costs, and deliver parts faster. So another thing, another couple slides here is one of our machines is at a large medical device OEM. Unfortunately, I'm not able to disclose who they are because they see it as a strategic advantage. They don't want everyone to know that they're doing this. But our machine is at a large medical device OEM, and they're using our printer pretty exclusively, extensively for product development. So with medical device industry, uh, when you're prototyping or doing FDA approval or things of that nature, you need to have an end use material for testing. You can't have some 3D printed plastic that you're saying, oh, I'm going to make this, but in a different material when I actually go and ship it. No, you got to have the actual material you're going to be using. So the ability to produce tools early on in the process that can actually mold these materials is really, really beneficial. So, one quick example here, this is the medical device tool, so this is the actual plastic part they're making. This is for a relatively low volume application that they were running. They were able to reduce the time to achieve this tool. They got very, very accurate geometry, and they were able to get production grade parts out of this process. So again, you can look at this time. They estimated it would have taken about 148 hours to build this tool. Traditionally, they would have to go through all these steps. With our process, they cut that down to just 49 and a half hours. And again, that insert can be printed in about 60 hours, but then it only needed a little bit of final finishing. They did a little bit of wire EDM for those ejector pins and things. So tool making down from 148 hours down to 50 hours, the ability to produce this tool in house. And you can see some of the metrics here. I love looking at these graphs and seeing just how accurate these tools are. Accurate within 0.001, and really, really great savings here. You can see lead time for them, 80% lead time. It would have taken them 7 weeks to source this tool. Traditionally, they're able to make it in-house in just 8 days. Cost savings, 50% cost savings as well. So that ability for this medical device company to really, really reduce the lead time for producing these tools, which they see as a huge strategic advantage, because for them, they want to get through the product development process as quickly as possible, as efficiently as possible, so they can be first to market, so they can have their products on, they don't want to be waiting around 10, 12 weeks for tooling. So Mantle is definitely integrating into some OEMs today, very, very, very successful in the medical device world, but certainly in automotive, consumer, all these other applications that people see this advantage of being able to mold parts in-house.
Nice. And I guess, before we wrap up, because we're coming close to an hour now, just looking into the kind of market dynamics of the tooling industry, and, I know we've covered it a fair amount, but looking at those lead times and skilled labor shortages in the industry, notably when the mold tooling is sourced from overseas, is there a sort of, the implication that 3D printing is having on that kind of issue to overcome?
Yeah, absolutely. So we're a part of an organization here in the U.S. called MAP, which is the Manufacturing Association of Plastic Processors. They produce a survey every year asking a variety of questions, some of which are about tooling, about lead times, about costs. I have a couple. Sorry, I keep jumping into slides here, but I have slides to speak to this. This is interesting to see. I think it's interesting, at least, that over the past 5 years here, you can see that the red is increasing, yellow is staying the same, green is decreasing. This is for lead time on tooling. You can see that essentially every year lead time is increasing or staying the same for almost across the board. Interesting to see that when COVID hit, right, and COVID was so severe in China that all those tool shops shut down, just spiking through the roof, the lead times and costs of sourcing tools, and still seeing those lead times going up. So incredibly long lead times for tooling, and we're seeing that continuing to increase. The same goes for cost. This is looking at costs for both domestic and foreign-based tool builders. Over half of the processors reported that, or sorry, almost 80% of processors stated that U.S. tooling prices were increasing or significantly increasing. Over half were saying the same about foreign vendors. But the thing that's interesting to look at, I'm playing my little economist role here now, is that molders are seeing double-digit growth every single year. So they're seeing more and more demand. They're getting lots and lots of growth. A lot of that coming from reshoring, people trying to bring manufacturing back to the U.S. But what this kind of implies is that the U.S. tooling market, and tooling is really lagging behind that of molding growth. If tool makers are making more and more money, their demand is going up, but their tool cost is going up and the lead times are going up. That means that there's more demand for tooling, but there's not a lot of supply for it. And a lot of that has to do with this labor. This is, of course, just looking at the United States here, but this is the number of tooling employees over the past 25 or 27 years here. And you can see it just dramatically decreasing year over year. Fortunately, a big reason that this happened was a lot of tooling went to Asia in the 90s and went to Asia in the early 2000s, where a lot of people that were in the tooling business retired and they weren't replaced because so much of the tooling was going to Asia. But now tool makers are starting to try to bring tooling back. Molders are trying to bring tooling back because the cost and the lead times have gone through the roof. Our technology we see is a really, really good fit for that, because if you can't invest in labor, you have to invest in technology. And we're one of those technologies that's allowing people to kind of solve this challenge and really have that strategic advantage of bringing tools into house themselves.
Yeah, and you were saying that the tooling industry is a lot of very skilled people who've been who are
Absolutely.
putting
It's
together their time.
it's it's years and years and years to train a tool maker, there's lots of things going on, with Society of Manufacturing Engineers and different people that are trying to encourage young people and people to go into tooling, and to go into the manufacturing industry in general. But it's got to be a two-pronged approach, I think, and technology is one of the big ways that we're going to be able to keep tooling in this country.
Yeah, no, and it sounds like this is making the tooling a much more approachable technology with those kind of transferable skills.
Absolutely.
Excellent. Well, I think we've gone really into the deep of it, which is great. I think before we kind of wrap up the event, we should go maybe into a couple more of the questions
Sure.
that the audience have been asking.
And I just
Um,
want to share this quickly as well. Just I'll leave this up as we're talking. Feel free to email me if you have any questions, thoughts, or comments, or want to get in touch with me. Always more than happy to chat. So I just wanted to put my email on the screen here. But let's get into some questions. And if there's something that you want to talk about offline, just feel free to shoot me an email.
Thank you. So one I saw popping up is somebody was asking about the diameter of the dispensing nozzle,
Yep.
and also the layer thickness available or
Yep. I
achievable.
believe I believe our nozzle is a 1 millimeter nozzle, so relatively large if you look at other FDM processes, but it doesn't really matter for us because we're going to come back and machine anyways, that we'd almost rather print relatively quickly and a little bit oversized and then come back and touch that up. The same goes for layer thickness. Generally in 3D printing, people try to use the smallest layers as possible because it's going to give you the least obvious layer lines. Again, for us, we're going to come back and remove all those layer lines anyways with machining, so we don't really worry about layer height as much. We want to obviously achieve the best layer height for our process. So we print at I believe, a 150 micron layer height, but we're going to machine that back to about 100 every layer to get that perfectly flat surface.
Excellent. And then another question following up and looking at the printer costs and the other startup onboarding and operating costs that
Sure.
someone might consider when when adopting the technology.
Yeah, so there's obviously some installation costs. There's some ancillary equipment, like you need a special refrigerator, to not overly expensive refrigerator, but a flame-proof refrigerator to hold our material. There's some replacement tools and things like that. If you want to send me an email, I can send you a more accurate, full startup cost that includes all the ancillary equipment and everything involved for that process. But there are a couple more startup costs, of course. But the machine is 230. The furnace is 120, so 350 total. The reason we break those out is because one furnace can support multiple printers.
Excellent. A material-based question. Now, somebody was asking what the approximate timeline is for the
Sure.
420 SS material to
Yeah,
be
I don't want to put words in our material science team's mouth. We're actively printing that material daily. We're getting great parts out of the process. I believe we're looking at that for about Q4 or early of next year. So actively developing it. If you have an application, reach out to us, because we're looking for some partners to evaluate that material and test that material to make sure that we're producing what the industry needs.
Okay, excellent. Did you see any others that you?
Yeah, so a couple interesting ones about repairing worn tooling. So our tools, once they come out of the furnace, you can certainly repair them the same way you would traditionally. You can weld them, you can grind them back, you can do laser welding, things like that to repair the geometry. We aren't able to put it back in the printer and print back on top of it. That's something that like a hybrid process can do, simply because it's a green body in the printer. It only turns into a steel in the furnace. So we can repair the part the same way you would traditionally, but you can't use our technology to repair the part. See another question about green material waste. That's very interesting and a good question. It means you understand our process well. Our cutting tools actually have a shroud around them that's pulling vacuum. So all the chips and dust are being pulled uh, through that shroud into actually a bag that's in the back of the printer. So you're not exposed to any of that waste. You're not that waste is not a concern, but it is hazardous waste because it has metal powder in it. So you would need to take that bag, close it up, and put it into either your hazardous waste, or you would need to get a drum from a company. We are beta customers that are using the machine at like 80% utilization, so quite extensively, are saying that they're having that drum fill every 6 or so months. So you'd have to get that picked up, but that's not a big concern because you can just schedule that with any hazardous waste company.
Excellent. Well, that about wraps up the questions from what I can see. Ethan, did you have any sort of parting words that you wanted to leave with our audience before
No, I
we
no,
the show?
just appreciate everyone's time and appreciate you coming and joining us today. Again, feel free to shoot me an email if you have any questions, thoughts, comments. I'll follow up with a recording and some other options. But if you're ever interested in evaluating technology, please don't hesitate to reach out, or have any other questions, don't hesitate to reach out. But thanks for joining us.
Excellent. No, and thank you very much, Ethan, for presenting on the show. It was really interesting and great to learn a lot more about Mantle.
Great.
All right. Well, have a good rest of the day, everyone.
Yeah, thanks everyone. Bye.
Bye. Take care.